सो ये प्रॉब्लम है थोड़ा सा इसमें. So I have sent you a link. I have sent you a link again. दोबारा जरा ये लिंक देखिएगा जरा प्लीज. Try visiting this link. So is it available now, the new link? Are you able to attend through the new link?
जी सर ये चल रहा है.
All right. So let's hope that it will carry on, right? So let's resume. Okay. So So the impedance 6 plus J2 is in parallel with this impedance minus J4, and we have removed this source. We removed or turned off independent source, right? So we need to find this impedance, the parallel impedance, the combination of the equivalent impedance of this parallel combination, right? So Z1 is then given by minus J4 multiplied by 6. So that will be minus J24, right? And then J square minus J multiplied by J. So that will be minus J square. So that will be plus. So 4 multiplied by 2, that will be 8. Right? So minus J4 multiplied by J2 will give us 8, right? Divided by so that was 6 plus yeah. So minus J24 plus 8. So 6 and 6 minus J2 minus J4 plus J2, so that will be 6 minus J2, right? So Z1 is given by, let's transform this into polar form to find the equivalent impedance. So 8 minus J24, we need to find the equivalent number in the polar form from the rectangular. So 8 and minus 24, when converted to polar form, this will be 25 angle 25.30, angle is minus 71.565, minus 71.565 degrees, and that is divided by 6 minus J2. So let's also convert this into polar form. So 6 minus 2, so that is 6.32 at an angle of minus 18.43 degrees. So Z1 is given by, then the magnitudes are divided, the angles are subtracted. So 25.3 divided by 6.32. So that is equal to 4, and the angle is minus 71.565 plus 18.43. So that is minus 53.14 degrees ohm, right? So this is the impedance, this impedance here, 6 plus j2 in parallel with minus j4, we called it z1. So this is this impedance. So let us convert this into the rectangular form also. So 4, and the angle is minus 53.14. So this is 2.4 minus J 3.2 ohms. So this can then be, this was figure, for example, 3, and the revised figure will be like this. This is this Z1, right, here, across this terminal A here, and then with this 10 ohm here, right, and this is terminal B here. This is A and B. So you see Z1 and this 10 ohm are in series. So Z Thevenin equivalent impedance is given by just simply Z1 plus 10 ohm. So the impedance part is, the resistor part is added here. So Z Thevenin is given by 2.4 minus J 3.2 plus 10. So Z Thevenin is given by 12.4 minus J 3.2 ohm. So this is the Thevenin equivalent impedance that we have found. This Thevenin impedance here is given by this value. So this can also be represented in polar form. So 12.4 minus 3.2. So that is given by 12.81, and the angle is minus 14.47 degrees ohm. So this is the Thevenin equivalent impedance, right? Now we need to find the Thevenin voltage. Let's look, before we find the Thevenin voltage, let's look at the process again. What we've done is, we have turned off this independent source to find the impedance, Thevenin equivalent impedance, and the revised circuit is given here. And from this circuit we see that 6 plus j2 is in parallel with minus j4. So 6 plus j2 in parallel with minus j4, so that is equal to minus j4 into 6 plus j2 divided by minus j4 plus 6 plus j2. So that is j minus j24, and then plus 8 divided by 6 minus j2. So this is then converted to the polar form, both the numerator and the denominator, for the purpose of the division. And after dividing, we find that the Z1, we call this impedance here, this parallel combination of impedances here, as Z1. So Z1 is equal to 4 angle minus 53.14, and expressed in rectangular form, that is equal to 2.4 minus J 3.2. So this Z1 is then here, this is in series with this 10 ohm resistance here. So Z Thevenin is the impedance, which is the equivalent impedance across these terminals, is simply given by the sum of both these impedances, Z1 plus 10. So that is 2.4 minus J.3 plus 10. So that will be 12.4 minus J 3.2 ohm, and expressed in polar form, this is given by this value, right? So now we are interested to find the Thevenin equivalent voltage. The Thevenin equivalent voltage is the open circuit voltage across these terminals, right? And if you see, when this terminal is open, there is no current which flows through this 10 ohm resistance, right? So this 10 ohm resistance does not have any current through it, so there is no voltage drop either. across this resistance. So the current flows like this from the voltage source through this branch and then through this branch, and the voltage here at terminal A is this terminal A, and the point here is the same as the voltage across E and B here. For example, if this is point B, let's call this as point C, for example. So as there is no potential drop across this resistance, the potential here is the same as the potential here, right? So the voltage VAB is the same as the voltage VAC. Let me repeat it again. There is no current flowing through this 10 ohm resistance, right? So there is no voltage across this resistance. The voltage drop across this resistance is 0. So the potential here is the same as the potential here. So it means that the voltage potential difference between A and B is the same as the potential difference A and C, right? So I can say VAB is equal to VAC, right? So what we need to do is just to find the voltage across this capacitor. So this can be done in many ways. One of the methods is using the voltage division, because when this terminal is open, then 6 plus J2 is in series with this minus J4. And remember, we do not make this assumption when we are calculating the Thevenin impedance. When we are calculating the Thevenin impedance, we assume that there will be a load connected here across these terminals. So in that case, we do not assume that this terminal is this resistance is out of the circuit, right? So this assumption is only made, or this method is only used when we are finding the Thevenin voltage, right? So VAB is given by the voltage, or we can just find the current through this loop and then multiply the current through with this impedance to find the Thevenin equivalent voltage, or we can use the voltage division also. So that is minus J4 divided by 6 plus J2 minus J4 multiplied by 30 angle 20 degrees, right? So VAB is equal to, this is minus J4 is equal to 4 angle minus 90 degrees multiplied by 30 angle 20 degrees, and this is divided by 6 minus J2. So VAB is equal to, this is 30 multiplied by 4 is 120, and minus 90 plus 20 will be minus 70 degrees, and 6 minus J2 we found here. 6 minus J2 is equivalent to 6.32 angle minus 18.43 degrees. So V Thevenin, which is equal to VAB, is given by 120 divided by 6.32, 18.99 angle minus 70 plus 18.43, that is minus 51.57 degrees volts. So this is the Thevenin voltage, 18.99 angle minus 51.57 degrees volts. So this is the Thevenin equivalent circuit here. Then the value of Vt is given by this voltage. The value of the impedance here is given by this Thevenin impedance here, right? And now if we want to, we connect any type of load here and then calculate the voltage across that load and the current across that load. And if we connect that load here, then across these terminals, the voltage and current will be the same as we have found here. So this is how we find out the Thevenin equivalent circuit. We can find the Norton equivalent circuit from this Thevenin equivalent circuit also. What we need to do is just to transform this, apply source transformation here. So the Norton current, for example, will be given by I Norton is given by V Thevenin divided by Z Thevenin, right? And Z Norton will be the same as the Z Thevenin. So for example, if we need to find I Norton, so then V Thevenin was 18.99 angle minus 51.57 degrees divided by 12.81 angle minus 14.47, right? 14.47 degrees. So I Norton is given by 18.99 divided by 12.81. So that is 1.48, and angle is minus 51.57 plus 14.47. So that is equal to minus 37.1 degrees amperes. That is the Norton current. And the Norton impedance, that Norton will be the same as the Thevenin impedance, and that is given by this value, 12.81 angle minus 14.47 degrees ohms, right? So we can draw the Norton equivalent circuit also like this. Remember that whenever you ask to find the Thevenin equivalent circuit or the Norton equivalent circuit, so after finding the values, must draw the circuit also. So this is I Norton here, and this is the Z Norton here, and these are the terminals A, B given in the original circuit. So I Norton is 1.48 angle minus 37.1 degrees amperes, and Z Norton is 12.81 minus 14.47 degrees ohms. So this is the Norton equivalent circuit, right? So this was figure 3, this was fig and 4, and let's call this fig 5. So this Norton equivalent circuit is found after we have found the Thevenin equivalent circuit. So using the source transformation, we have found this Norton equivalent circuit. We could have directly found the Norton equivalent circuit. The impedance is calculated the same way as the Thevenin impedance, and for finding the current, we just short circuit these terminals, right? We short circuit these terminals A and B, and then we find the current through these terminals. We can apply mesh analysis, for example, one in this loop and the second this loop, and then we need to find the current in this second loop. This current in the second loop will be the Norton impedance. So this is how we Norton current, sorry. So this is how we find the Norton current. So if you have any questions, you can ask me. We can switch off the stream, then you can ask the questions, please.